In this lab, we are exploring how the drag force and weight force interact on an object by using Newton's second law and the position function to predict the motion future. The objective of the lab was to pick and observe an object falling from rest and analyze its motion by considering different forces at work. I chose to observe the motion of a parachute man that is dropping from rest. To analyze this motion, I created one computational model that simulates the gravity of the skydiver's motion and another computational model that simulates the effect of gravity and drag on the skydiver's motion. I compared the models by plotting the observed and predicted position versus time. Modern skydiving is usually done in a high-altitude, low-opening halo method. Skydivers usually drop from an altitude of 7,500 feet to 15,000 feet and pull a parachute 2,500 feet from the ground. Many different factors play into a skydiver's descent. Many parachutes are made from strong nylon used to withstand the force of the air's drag force. However, our parachute toy is simply made from plastic. I used Newton's second law to help me predict the motion. I considered the effect that the drag force and gravity each had on the parachute man as it fell. Newton's second law states that the acceleration of an object is directly proportional to the net force acting upon the object and inversely proportional to the mass of the object. As you can see, the parachute man falls from rest and moves in the negative y direction. Time is plotted against the y position. I used this measurement to calibrate length for the video. Initial conditions, including the initial velocity and time, were inputted into PHYS from the tracker data. Since the parachute man is initially at rest, the initial velocity is 0. To find the value of b, which is a proportionality constant, for the magnitude of the drag force, I found a number through trial and error that gave me the same final position as that in the tracker. The weight force or gravity has to be accounted for. This is equal to the negative mass of the parachute man times the magnitude of the weight force, 9.8 newtons over kilograms, times j hat, which is the unit vector that gives the weight force vector its direction. The negative comes in because the gravitational force on the parachute man is in the negative y direction. The drag force is the air resistance on the parachute man. In this lab, the drag force is modeled as being the opposite direction of the weight force in the object's motion, and the magnitude of the drag force is proportional to the square of the object's speed. This can be presented by the equation where b is a proportionality constant. The magnitude of the velocity is the speed squared times j hat, which we defined earlier as being the positive y direction. Newton's second law and the position update function allow us to predict the future position of the object as time progresses. Here is a graph comparing the experimental results from tracker with the predicted results from both the drag and weight forces and just the weight force. The line showing the drag force and weight force followed the experimental results more closely than the weight force line does. The final positions in the graph, like the initial positions, were not predictions because I calculated the b by getting the final positions to align. PHYS has a slight discrepancy in the velocity of the parachute man here. The discrepancy could easily have been due to the force of the wind causing the parachute man to fall incorrectly. Terminal velocity is the constant speed that a freely falling object reaches when the net force is 0. The graph is a position versus time. However, when the slope of the position is linear or constant, the velocity is constant. It looks like both of the model curves are linear at the end, thus the velocity is constant here. The curve of the drag and weight forces will probably be more linear over time because the drag force will eventually equal the weight force, as the PHYS model arrow showed. What effect does the temperature and air density have on the skydiver? Air density and temperature does not play a role in the magnitude of the terminal velocity. However, a skydiver can reach terminal velocity faster or slower depending on the air density due to temperature, humidity, and altitude. What effect does the shape of a free-falling skydiver have on the speed of the descent? Drag force is dependent on the shape of the skydiver. The drag force decreases by the skydiver assuming a more aerodynamic position. Drag force can be increased by increasing the cross-sectional area with the body or by pulling the parachute. Note the diagram demonstrating the body's position versus the force of the air. In conclusion, both the drag force and weight force were acting on the skydiver as he falls. The effect of the drag force was not as significant as the effect of the weight force. Thank you for watching.